the idea that when we, so the information bottleneck concept, the idea that when we build a representation, we seek a compressed or minimal statistic representation of the information content of the data that is relevant to the task at hand. So in this case, relevant to the outputs that we're trying to generate. So I found that that has dramatically affected my thinking. And in that context, so information theory played a big role in there because it dealt with the notion of compression, sufficient statistics, and so on. And then the interesting question as to the fact that there are an infinite number of ways in which you could represent that compressed representation. And that each of the methods we apply seeks to build a representation in a different sense. And then the question becomes, how do you map between them? So a physics-based representation might use a different compressed representation than a purely data-based representation. And so then you end up with this challenge of how do you interpret one in terms of the other, or translate one to the other, or how do you constrain the process so that it gives you a representation that has properties that you like.
Yeah, I think, I mean, that was a pretty powerful idea and covers a lot of grounds. How do we take it into, say, our world?
I have some ideas, but I'm waiting for somebody else to say something also. So one of the things that was going through my mind this morning as I was waking up was the idea that when we build a model, we have this paradigm that we use in the literature and the earth sciences where we talk about uncertainty. And more I'm uncomfortable with the notion of uncertainty. Not that I don't think that it's an interesting idea, but in the sense that when we build a representation, as we build compression, very often what we're doing is something which is lossy. In other words, we're losing information. And so what we call uncertainty, to me, is really the consequence of lost information. Information that either is lost because it's not properly captured by the data, or because we choose to build a simplified representation of the world, which is how I think of models. And then in order to account for the fact that our model predictions don't match the data, we then impose on top of it this idea of something that we call uncertainty. And what's interesting to me is that our models are always crisp, and our representations of uncertainty are always crisp also. Whereas what I think of in a subjective sense as uncertainty is usually the fact that I'm not actually sure about the crispness of that representation of the model, or the crispness of the representation of uncertainty, the probability distributions or fuzzy distributions, whatever I put on top. And so what I like about the information theory perspective is it forces us to think about missing information, which I think is more powerful than just thinking about uncertainty.
Yes.
Thoughts, reactions?
This is Hernan Moreno from University of Texas. I really like the Hoshin's reflections on the problem of the issue of representation, and how can data science or statistics help us find relationships that have not been perhaps observed through the usual methods we use to observe or describe nature. However, the issue of representation is really critical because the things that we know that happen should be really represented by the physics, the equations that we have of or the expressions that relate those variables and those states. But then it is statistics or data science. I think that's a tool that's going to allow us to observe the things that we haven't been able to observe in certain way. But as far as we don't represent those processes well in our, and I'm referring about hydrology specifically, or climate models too, as far as we don't represent well the geometry of our domains, for example, we're not going to be able to resolve those partial differential equations well, so that the physics is very well resolved inside. So first of all, we need to better represent our models, perhaps considering some adaptive means to do it, not very rigid approaches like making all the domain as fine as possible, but perhaps making it fine when it is necessary to be fine and coarse when it is not necessary to be coarse, so that the processes are correctly represented where what is necessary, and we're only getting redundant information. We shouldn't do that. But then the other problem is the physics may not be able, to capture, even though if we improve representation in some models, there may be some missing observations or some missing information that it's still not captured by improving the representation of the models itself. That's when I believe the science of the data could help us understand perhaps a very random process that we haven't been able to account for, or some other effects that in complex sciences like climate or hydrology, in which a lot of processes are in play, we haven't been able to discover or simplify into equations. I don't know, those are my thoughts. Thanks for listening.
Sorry, the jackhammer is still going here, so if there's a lot of background noise, that's why. They're outside, so I can't even ask them to stop. I thought it was interesting that you mentioned the question of, does redundant information help to improve the representation of models? Because I think that's kind of like, I wouldn't say a finding that I've had recently, but I found it out for myself by basically looking at just generating models just from weather station data or something like that, and time periods in which the sources are more correlated to each other led to better model performance. And the only explanation for that is that a model that wasn't properly accounting for one of the sources due to its correlation or dependency with another one of the sources caused the model to perform better. So it kind of allowed for the model to sort of compensate, for some of its shortcomings because of the sources being dependent with each other. Whereas when the models are independent, or when the sources are independent, then you have the case where it's kind of the worst case model performance. And that's kind of related to, I guess, this series that we've been having all year. One of the things that I'd kind of been thinking about beforehand and trying to link everything to is how our models processing information from multiple sources, or how are multiple sources coming together and influencing processes as we observe, and then as we model them. And kind of the question of a physically based model versus a data-driven model what's the real difference if they both reproduce the types of interactions that we see between our inputs and our outputs? So things like if we just consider it as the PDF, so if we just look at a PDF of all the sources and the output, and maybe it's a high dimensional PDF, and if one of them is the same, if two are the same, I guess what does that say about how you originated that model? Or is it a physically based model, or is it some type of data driven or some type of AI type of model? So that sort of links together the papers that are the framework on causality paper that kind of digs into those detailed levels of interactions between multiple source variables. And I kind of thought about how that applies to modeling in terms of how these multiple sources are interacting in different ways, depending on what type of model framework you have. So it was just kind of one thing that I've been thinking about throughout the year.
Can I ask a question about that, Allison? So much in the way that in physics, this is kind of a devil's advocate question. In physics, we have, at least for the time being, decided that we're comfortable with the characterization of light as both having wave-like properties and particle-like properties. If I were to give you two models, one a physics conceptual explanation type model and another purely data-based model, let's call it an information theory-based model, although perhaps that's not the best separation. And they both predicted the behaviors of the systems equally well. What could we infer from that?
I guess it depends on what equally well means, right? So are they exactly the same? Do they produce exactly the same output?
Let's argue for a moment that they can produce exactly the same output. I agree that that could be fuzzy, but
yeah. So if they produce exactly the same output, and all you have is the input and the output data, and you don't know anything about the two models, but the output data is identical, there's nothing you could do without any intermediate information, right?
So how would we as scientists accept those two models? Would we accept one, the physically based one, just purely because we understand it and reject the other one? Or would we be required to hold both? And what would we do with them if we held them both?
I mean, would that actually mean, though, that your data-driven model is figuring out your process-based model, and it's actually, if you were to put it in AI Feynman, it would come out with the equation that you actually used to
No, I'm not looking under the hood so much, but I'm, the current thing basically says we look at a data-driven model and we don't understand why it goes from A to B or X to Y. Whereas we look at a physically based model and we believe it represents causality and it uses objects that we think are physically relevant. And it represents relationships in ways that we think are meaningful, right? But both, and we don't have this situation right now because the database models invariably do better than the physics-based models. But let's put this hypothetical situation that they both did equally well on all possible data sets that we tested them on. What would we actually do with that, and what would we infer? Yeah. I guess that's my question.
Roshi, can I comment on that one? Because I'm, so my research right now, I am in, can you listen to me?
Yes.
No. Okay. So I was wondering, I mean, I have worked during my entire career with physically based models, parallelized supercomputer models, very expensive computational wise. But if you have two models, right? One is data-driven, the other one is physically based. When we were talking about the book of Dr. Chiara Marletto, my idea is, okay, so you're getting this information for the physically based model, right? Can you transfer that to another phenomenon? Whether it is in an explored area, it could be just, for example, I'm using turbulence and advection diffusion equations. So I have been using that for fluvial geomorphology in river science. But let's say, you have to apply the same momentum and advection diffusion equation in a contaminant plume and how that disperse off or advect. So when you have, your methodological study, that is, you are applying your physically based model, you are analyzing that with data, probably you just use both. Can you transfer both models to a phenomenon that you don't have any data? You don't know well the phenomenon. You know that, there are some physics there, but basically there's a lot of uncertainty, not in the model, but in the conceptual process itself. So I don't know if at that point, then you have a benefit coming from the fact that you understand the physics versus if there are no data. So how can you really get prediction or any type of information from there? So just talking about those counterfactuals and whether information can be transferred. If it cannot be transferred, then it is not information itself. I don't know. I was just thinking about along those lines. And
yeah, I think that's a very good insight, because what you're suggesting is that the role of modeling is not just to map the inputs to the outputs, but to learn something and then learning something means you can then transfer that information into another context.
right.
So I think that's very interesting. And the second thing you mentioned was the ability to develop counterfactuals, which again requires some kind of contextual basis for your representation. In other words, your representation is not out of context. It's always in the context of everything else that we've learned, not just in the context of the data itself. So I can just take a data set and I can build a mapping, but we want the mapping to also somehow refer to other mappings between other data sets that we might be interested in working with, so that we can ask what if questions, and so we can transfer it. And transference is a kind of a what if question, right?
Right.
So transferring is like a counterfactual in some sense. Yeah. I like that.
Well, in that context, then data-driven models are not going to be that applicable.
So what's the value? So what would the value of the data-driven model be then?
I think that
the value. Go ahead.
Sorry, go ahead.
No, you do. You have something on your mind. I'm just.
No, I just wanted to add, like, maybe it may also depend on the application in hand, because sometimes, there is computational complexity that comes into play, which and also, I think data-driven models may have other advantages. You can test different things. You can do different types of Monte Carlo simulations with that, just to give an example. But if you have a fully distributed convection permitting model, for example, that thing probably is not possible to do. So that was just like a comment on this. But going back to Hoshin's example, that hypothetical example, Hoshin. So do you think that is there a possibility that, the both models are performing exactly the same way, because those particular physical processes that the physics-based model is representing, the data actually holds adequate information to represent that through a data-driven model, right? Can that be a reason why the performance is so similar in that case?
Arguably, my example of light being particle and wave is not the perfect example, because you could think of the blind men and the elephant, and you could say that each of the blind men has only a limited perspective on the elephant, And so they both see the same thing from different perspectives. And so in that sense, the representation is not complete. But what's interesting is if both the representations are complete in the sense that they both explain the data equally well, then it raises the question as to, is that representation complete? You know, what does it actually mean that I can do the same thing in two different ways? Is it really possible for me to express the same idea equally well in both English and Chinese or Hindi? And I was thinking of you, Roy, because you're interested in taking hydrology learned on Earth and applying it to Mars, right? So that relates to the transferability and the counterfactual issue that Laura raised.
My question is for you, Hoshin. I mean, when you are transferring, right, those models and to represent another planet, for example, for Roy, is the data-driven model is still useful in that case? Or you just need to, you know, say, here is what I found in Earth, but in order to represent it in Mars, either you need the same data, and thinking that, you know, the same amount of data, you will get the same outputs as well as the physically based model, or you just need to say something like, okay, I mean, to represent the same processes in terms of hydrology in Mars, I just need the physically based model, because there's, you know, the data driven, I'm wondering if it's very related or just very specific of a process in one area, in one domain. So in that sense,
yeah, I'm not going to speak for Roy, so I'm going to push it back on him.
First of all, so this is a project that is not funded yet, so we haven't actually started the work. But you know, we have been thinking about this problem for a while. Now, from my understanding on this, every model is in a way data driven, because you know you have to basically make it work. You need some sort of data to support. I mean, every model uses parameters, and many of them are abstract parameters, right? The concept of physically based model itself is tricky. Now the question is like how much data you need, how you can use that data. So going back to your question, Laura, yes, I mean, in that cases, you don't have sufficient amount of data to really train a neural network, for example, or this type of model. So you have very limited observations or whatever information you have. So the idea would be to kind of like start top down. So you start with, you know, governing principles. You look at different trajectories, like how the models evolve, and then you can use whatever data you have to constrain your models, right? So that's one way to look at this thing. So you constrain the trajectories and you sort of reduce that, you know, the range, that uncertainty in that process. So so the idea would be to still use the data, whatever data you have, but maybe in ways that, you know, a small amount of data can add a lot of value. So I think the way of implementing or using data in a model itself is a big challenge, and I think all of us are probably dealing with that in some form or the other. Yeah.
What else stands out for people in our readings over the past year plus? What other ideas influenced the way you were thinking about the world and your work? I'm sure everybody here has been influenced in some way or another, otherwise you wouldn't be at this meeting. So what's the very first thing that comes into your mind without censoring it and thinking it's not important?
I guess for me, Kratzert paper and the comparative performance between data-driven and physical models. And okay, so if we have a neural network trained with a range of parameters that covers the that covers ungauged basins, well, we don't need to have we can predict we can predict runoff better than some benchmark physical models, as long as in some other I guess some other basin that's in the training set has or covers the characteristics, and also with that the information content of the static basin characteristics. That really has been on my mind.
So what do you think that implies? I mean, what do you think we've learned from that?
I guess maybe it's hopeful, but yeah, you don't necessarily have to have how do I say it? You can predict out of sample, to say it bluntly. Yeah.
Using a database model, you mean? What do you think it is about the database model that enables you to predict out of sample?
I really don't
In other
know.
words,
I really don't.
I mean,
but I guess my hunch is that it is coming up with models of processes and their interactions, and it's accurately describing interactions between processes.
So there's some relation to counterfactuals there, right, Dan? Because in a sense, you can't address counterfactual issues unless you have a representation that is good enough to facilitate that. Right? And predicting out a sample, we're relating to be a kind of a counterfactual type of thing. So right? What would it do under these circumstances?
Yeah. So something like predicting runoff in a very dry, high elevation. I'm just thinking of a very like a toy example, but high elevation, very dry basin. We don't have one of those in our data set, but we have a few dry basins, and we have some high elevation basins, but the specific combination of characteristics we don't have. So if I can, but we know that the counterfactual is that we don't have this specific combination, but it could exist.
So if I can push on that thread a little bit, I happen to have inside information. So I know that Jonathan Frame has just submitted a paper to Hess where he tested LSTMs against the SAC model and the National Water Model for predicting extreme events. And he trained the models, as part of this paper, he trained the models on data where the data included years only with less than 5-year return periods. And then he predicted on data which included events with larger than 5-year return periods, right? So he's predicting events out of sample. And gets a fairly consistent result that the database model does a better job than the two physically based models. Something which the holy cows of hydrologists were always, well, database models only are good at interpolation and they won't do well out of sample. So what do you think that tells us about anything? if that's a consistent result. I'm not saying it's one study, but what do you think that tells us about the value of information theory tools and how that might support physically based modeling or better understanding?
Question, but that depends on the physically based model, right? Because not when you talk about a physically based model, it's supposed to be physically driven, and sometimes you end up with some parameters that because you cannot explain them through physics, they quite of like get a lot, well, like some of them, for example, range in orders of magnitude. So if you think you have a physically based model that is based on parameters with a high range of values, just because you couldn't add more complexity to your model, then your physically based model is not that meaningful, and it's better to just train a neural network, especially if you have a lot of data, because that's something else, right? Like data analysis and how robust is your data, it's gonna depend how well you're gonna train your neural network, and your physically based model is gonna become more accurate if you don't end up in parameterization.
Yeah, but Mike, the question I'm trying to push on is, you have a very detailed physically based model, like the one that you work with, yeah? And somebody comes along with a database model and shows that the database model performs better out of sample.
Okay.
My question is, what are we going to do with this information? We got one which has really good, we think of as good understanding built into it. And we got another one where we have difficulty understanding what's inside. It's kind of black box, but it does better out of sample. The challenge for us as scientists is, what are we going to do with them?
Can you use a hybrid model that is either, the physically based model enhance your data-driven model, or backwards? At the end, it's a matter of the scale. So if you have a time scale and you just want to see all the processes that occur at every time step, that's something that the data-driven model may not be able to do, because it depends on inputs, outputs, and the final results. So
I think Alison has some thoughts on that. Yeah.
Yeah, go ahead.
I was just going to say that, I mean, to me, that indicates that if your data-driven model is performing better out of sample conditions it wasn't trained on relative to your physically based model, I mean, to me, I guess that kind of indicates that your data-driven model is capturing a process that you're not doing a very good job at capturing with your physically based model at all. So, you could argue that your data-driven model is becoming a physically based model if you could, make some interpretation about what it's capturing or what it's doing that you could convince yourself that it was physical. Then, it's almost like you need a new physically based model to better capture that type of interaction that is obviously happening at both, I forget what the context was here, but like both low flow and high flow conditions or something. It's like the same type of interaction is happening, right?
Yeah. I would say I have a complementary way to interpret the problem is that I would do another experiment or a set of experiments and see if the results hold up. Because it's to me suspicious that the machine learning model perform on the physics-based model. I'll do more experiments.
One thing I would add that is like the one way to make this an opportunity would be to see. So when we see that the machine learning model performs better out of the sample values, that means that process is attainable. That means there is predictability in the data. So that sets the stage to go back and sort of fix our physically based model and see what processes are missing and in where exactly we need modification. So I think these are not really competitors. Sometimes these are complementary, right? Yeah.
It's something with a circular kind of approach where you use your model, and if it behaves better out of sample, then you fix what you think the base process was not getting correctly, and then you tested again with a new set of experiments, and then it's kind of a circular version of improvement.
I mean, to me, what jumps out is the first question I would want to know is why, right?
Well, in this case, maybe it may be simply because your physically based model is not good enough. I mean, the process representations are not, I mean, a model being physically based doesn't always mean that it's representing the physics always accurately, right? There are different ways of representing a same process. So maybe that combination of parameterizations and parameters are probably not good enough in that context.
Or maybe it's because of you were saying at the beginning that uncertainty related with loss of information. So maybe we are using, we are putting a lot of uncertainty on the parameterization of the models. So we are not able to transfer all the information that we should have for that model to behave as a phenomenon does. But then I have a question. Yes.
If I could just mention, I'm a little cautious of any attempt to throw the baby out with the bathwater, right? Because there could be one small thing you've overlooked in your physically based model, which you've resolved. Everything else might be fine, right? And going back to what Martin has pointed out, you know, you've got so many hypotheses built into a physically based model all put together. It's very difficult to isolate the individual effects of each one. Sorry, go back, Leela. Yeah.
Yes, no, that is a very good point. I was about to ask how you were saying at the beginning. Let me go back to the notes here. You were saying that information theory perspective help us think about uncertainty as loss of information. But then if I think an uncertainty in the usually way that we do, then I think in probability. So, you know, from if you have a 0% match with a phenomenon or a 100% match. But then if you think on information, how do you know that you are getting the whole possible amount of information available to inform that process? So for me, I do agree that uncertainty can be seen as loss of information, but to what extent you're gonna have 100% of the information.
So I was saying,
sense?
yeah, I think the term I prefer to use is missing information rather than loss of information, although we can also talk about loss. So my question to you is uncertainty to you an objective concept or a subjective concept?
No, it is subjective. Yeah, because it is subjective to the conditions of the process that I am evaluating.
So to me, missing information is an objective concept, right? We can actually measure missing information. And to me, this sort of separates the subjective aspect from the objective. I could be not completely correct here, but that's how it's falling out in my brain at the moment. So if I don't have a model, I don't have any data, I have effectively infinite uncertainty. I could have a theory, which could be based on no data at all. And I could be perfectly certain and completely wrong, right? So this uncertainty seems to reflect more my confidence in something. Whereas I like the information theory perspective in the sense that it brings an objectivity to the study, and maybe we can separate out the parts of what we're not sure about due to objective factors and subjective factors. I don't know, but that's a hypothesis.
Another thing that resonates with me, I don't know if I can move to the next thing, it was the concept of knowledge in Chiara Marleto's book. And what she said that is the information that is capable to propagate, to conserve, and preserve it. So that resonates with me because I think that that it would be amazing to have like a formula or a DNA of some of the processes where you know that the information that it's able to be preserved of certain phenomena, and then propagate that information to, I don't know, to better explain the other phenomena or related phenomena. So yeah, I just want to put that on the table, the concept of knowledge in Sheraton.
So you're raising the fact that Chiara Marleto's definition of knowledge was a powerful idea that has been influencing your thinking, where she defined, if I remember correctly, knowledge as being self-preserving and perpetuating information. Something like that, right? So how has that affected you? The way you think?
I guess from how I see things, I want to see what is the elemental structure of how a phenomenon behaves. So I think in that way has impacted me. Because there are some phenomena that are difficult to explain physically, like to parameterize. So maybe using another perspective where you can account for the amount of information and the structure of that information, then maybe you can find the knowledge encapsulated in that information.
So if I can relate that to our previous conversation, if I take a physically based model, I might push back on me, guys. I might argue that our ability to represent the world in terms of physics is a kind of perpetuated knowledge. Whereas if I build a database model of something, it's not clear to me that I have gained anything that is self-perpetuating, unless I somehow cause it to be so. You know, I'm more likely to transfer knowledge from a physically based model in my daily life or my research than I am from one from a database model. Does that make sense?
So I'm going to jump in here just a little bit. Part of this thing is, I'm struggling with this duality or the necessity of this duality between physics-based and the database approaches. I don't see why it's an either-or situation, right? Part of it is just practicality. I mean, with our critical zone observatory, we are pretty much dealing with this in a recursive manner. New data points us to lack of knowledge, and that then leads us to design of new observing approaches or pointing to something new that we may not have observed or may not have paid attention to, and so forth, and go from there. So this under item 2 in that document, I just put some statement which I hand wrote a couple of weeks ago, and basically saying that every measurement involves an explicit or implicit hypothesis. This hypothesis essentially determines our choices, what to measure, when to measure, how to measure, how frequently to measure, etc. It also determines what we exclude, what accuracy is sufficient for the intended purpose, right? So data is not vacuous. I mean, it has a context. So the hypothesis may be constrained by the constraint imposed on the measurements, location, timing, access. I mean, there are a whole technology and so forth. So any scientific interpretation we make based on these observations may not just acknowledge what is seen from the data, what we call the data-driven approach, but what is unseen explicitly or implicitly due to the experimental design resulting from the underlying hypothesis. And the underlying hypothesis is basically framed on prior knowledge or whatever we have seen. So I say this can be seen from the eye of a counterfactuals. What hasn't happened but is possible will not be observed and may not have informed the hypothesis underlying the experimental or model design. So both the data-driven and the physics-based approaches suffer this. What is not observed may not be incorporated in our thinking and is not going to do anything for us. So is one of the key questions is how do physical and data-driven approaches reconcile this rather than being two different aspects that do not converge? And is there a mechanism for us? Because I think as hydrologists, we are too tuned to thinking that we are putting in a weather station and we are putting a stream gauge in a station, and that's all our measurements. We think that we don't have capability to adaptively and recursively do more detailed observational design, both in space, time, or choice of variables and parameters and so forth, right? So I don't know, I mean, this is a natural bridge between what we were talking before or this new topic, the intersection or union space between IT, machine learning, and AI. But I somehow think that those two are linked and there might be an opportunity here. So could what we are discussing help us overcome this thinking of that these are two dual things and we cannot reconcile, but is there an opportunity for us to help reconcile this? I'll leave it to that.
I mean, that's like a big missing information question, right? So it's that we have some sort of assumption when we take measurements that these measurements are the ones that are informative of whatever other measurement we take, and it's not, obviously. So there's missing information inherently in our observations. So we, even if we had the best model in the world, given those inputs that we measured, we wouldn't be able to perfectly reproduce our observed output.
Right.
And no model, whether it's physically based or data driven, is going to come up with that information that we didn't measure, or we didn't take some observation that we could have, or what we measured isn't actually the most relevant thing that we could have measured. Yeah, I don't know.
So that falls in the category of uncertainty about the representation, right? I mean, I completely agree that all data presupposes a representation. In fact, I just sent this to Praveen yesterday, but there's a paper that we might choose to discuss maybe sometime called On Crashing the Barrier of Meaning in Artificial Intelligence. And I'll just read you one idea from there, which says that understanding is built on innate core knowledge, which forms the foundation. Well, let me put it in the chat window, then you can all read it as I'm saying it. So understanding is built on innate core knowledge, which forms the foundation for future understanding, inference, and common sense. And that core knowledge includes, not complete, not comprehensive, an intuitive understanding of physics, how objects behave individually, how they interact with other objects, and the possible effects of such interactions, and innate metaphysics, notions of discrete objects, relationships, events, and causality. So we presuppose that we can think of the universe in terms of discrete objects, relationships, events, and causality. And in intuitive psychology, which includes concepts of what communication is for and a basic theory of mind for other humans. And so all of this underlies all representations that we build, including the representations that we use to collect our data. In this context, I'm reminded of a very interesting TED talk by a gentleman, I can't remember his name, but he pointed out that why did science survive as a way of explaining the universe, whereas mythology, Greek mythology, fell by the wayside? Well, some people still prefer Greek mythology, and in the context of what we're talking about, I'm going to rephrase what he said. But he basically said was that a good scientific explanation has to be able to withstand many difficult tests. And when you get a new observation, which is not well explained, when you get a new observation, it should not be easy to twist or bend your scientific theory to explain that observation. So a myth, a mythology, an explanation for why winter comes on the world, if you can just go ahead and say, hey, well, it's because so-and-so is very sad, you know, today they're very sad, or in the winter they're very sad, therefore the universe is cold. The world is cold. It's too easy to modify that explanation. And his argument was that scientific explanations are ones that are hard to modify. And that when we come up with new observations, which are difficult to explain using current observations, when we do come up with a new representation, a way of explaining those observations, that's a very major thing. It's not something that's trivial as just saying, oh, well, yeah, all we have to do is change the value of this parameter and we're good.
I wanted to add something else to what Praveen and Allison and Hoshi said before regarding going back to the analogy of models and reality. So data science and physics-based models. The very first example that Hoshin raised on why do some machine learning models outperform physics-based models? It goes to the typical question, or the question how to improve physics-based models, basically through three methods. And this reflects on Praveen's reflection. Number one, physics-based models might be lacking representation itself. Structurally, they might not be connected the way they should be inside. Second, the parameterization of the models may be wrong, and that's a source of uncertainty. But number three, I think this is what Praveen was referring to, is the inputs to the models themselves are not appropriate ones, or are lacking some more information that then feedbacks into getting better representation and better parameterization of the models themselves. So it's something that improves not only from the input, but all the way through the structure of the model. I'm talking about the physics-based model, which I think are the ones that we need to continue to develop. Even though machine learning is outperforming, we need to still learn from those outputs. But I think that's my recollection so far, and I'm trying to apply everything to physics-based hydrologic modeling, because that's the area that I do. But many of you may have some other analogies in your own areas.
So Hernan, how would you know that the data are not adequate? What's your perception of that?
Yeah, so that's so this is very intuitive, but when I see an equation that has a lot of exponents and coefficients, then I presume something is not very correct, because we're not depending on the continuity and momentum equations per se, but we are somehow using a simplification of those equations. And that means to me that we need to learn more, and we need to start creating more fundamental. We need to do more fundamental work. But then again, how can we do this if we don't know the exact equations? And then here is when data science and machine learning can help us out. But this relates to what Allison said before. This is something we haven't observed yet through the eye of our predecessors who built these empirical models, a lot of them to relate evapotranspiration to leaf area index or NDVI. I mean, that to me, it's an oversimplification of the photosynthesis process and the transpiration that occurs afterwards. So, so there's still a lot of missing information in there, but I think that's when data science and machine learning can help us out, filling in the gaps and trying to, first through correlations, which seem to be something simple, but it's powerful. But then try to transfer, generalize the knowledge with more and more and more and more and more and more experiments, which is our judgment is based on data, inputs and outputs. That's the best judge we have. Reality. Yes.
Let me ask Yuan if he wants to speak about this, because I think some of his research might have some relevance. Yuan, do you want to say something?
About what?
About the insufficient information content of data and how machine learning can help us learn about that?
Insufficient.
I was thinking about your LSTM models.
Mm-hmm.
I was thinking about your models where you used only P and T, and then when you used 6 meteorological variables, what you learned from that.
Oh, I think I learned from that is.
But you have to explain. I know what you did, so you have to explain to people what you did.
Okay, so basically I do an LSTM model to predict the snow water equivalence. And I use 4 different combination of input forcing. And so first one is I only use precipitation and temperature. And the other is I use 6 meteorological variables, include precipitation, temperature, and vapor pressure deficit and radiations, etc. And the other 2 is these 2 of each combination, and I add the elevation into it. But the results shows that the 6 meteorological variable one is has the best performance. And what I learned is I feel the representation of the LSTM, which means the composition of the upper range, additive, divisive, and the gating operations, these kind of things. It's more they are more, because okay, for Freddy's research, because they are doing the CAMOS data set in US, they only have like 500 or 600 catchments. But because my research is dealing with 0.3 million pixels, so I have a lot of data. And what I found is actually LSTM is more smart to use the information for the meteorological variable instead of the static features. And I think it's because the way the upper range, the composition of the upper range, how it processing the information, that matters. Because I think I'm not an expert in LSTM, but I think the motivation.
Sorry, Yuan, we lost the last thing you said because the sound broke up.
Oh, so what was the last thing I said?
Your last sentence, yeah.
Oh, so I think what matters is the composition of the upper range of the LSTM, how it processes information. Can you hear me?
Yes.
Yeah. So because maybe the idea of the LSTM was originally trying to processing the time sequence data, so it is more wisely to use the information from the time series data instead of the state features. Yeah, that's what I learned. And I feel to process different kind of data, you might need a proper model to help you to do that. So yeah. So what I learned so far is if I want to improve the predictive performance, then I will add the meteorological variable rather than the steady features. Yeah.
Thank you, Yuan.
Oh.
If I could just summarize a little bit of that. He was comparing with Snow 17, which uses only precipitation temperature and elevation. And he's building a model for the continental US. And some interesting things he found was that an LSTM, which only used precipitation and temperature, gave much better performance than Snow 17, which uses only precipitation and temperature. And Snow 17 was also given elevation. And Snow 17 was calibrated individually to every pixel that you were comparing to. Whereas the Snow 17 model, without being calibrated individually to each pixel, just with one set of parameters and model structure for the entire conus, is giving better performance. Okay, so that's the first part. So that's the that's the database model compared to the Snow 17 physical conceptual model. I won't call it a physically based model because it's a temperature index model. One model is a conus-wide single structure. The other one is the structure calibrated individually to every location. The second part is he then added 4 more meteorological variables to the inputs of the LSTM. And he found that elevation information was no longer useful. So the information in the meteorological variables arguably encodes everything that elevation was telling us about what was going on. And the performance of the model using 6 variables was better than using only 2 variables. So in a sense, that was a pointer to the incompleteness, insufficiency of precipitation temperature as variables representing the dynamical snowmelt. Now we know this to be true, but I'm just using this as an example of how a data-based approach might throw some light on physics.
Yeah.
And
Yeah,
also-
this is great.
Well,
So do you
sorry,
think
go
that,
ahead. Sorry.
okay.
Go
Go
ahead,
ahead.
Alison.
I was just going to ask, the meteorological variables, are those a function of elevation themselves? Like, were they derived from like using an elevation data set, I guess? And that would be a thing where if you had a meteorological data set that wasn't a function of elevation, maybe you'd get something different.
Yeah, I think looking at the multi-collinearity problem in the data, in the input variables is a good start. And then so, and that way we can get rid of the redundant ones. Yeah.
But how does this relate to Allison's question, which was she pointed out that the redundancy in the data, the actual correlation, was actually useful in helping constrain the development of her model because it gave her something useful to work with. What do you think about that, Allison?
Yeah, that's interesting. That's related.
Alison, was that correlation between input and output or within inputs?
I was thinking the inputs because elevation is related to all those meteorological variables. Thus, they provide some redundant information, which if your model is good in terms of it's doing the right physical representation, that shouldn't matter. So you could get rid of that redundancy, right? So you could say that, our meteorological variables completely encapsulate all the information about elevation that goes towards estimating whatever we're estimating. But in reality, maybe your model is not as good, and maybe some of that dependency between your meteorological variables and elevation is actually useful to help your model perform better. Maybe.
Mm-hmm.
Well, we would expect from physics that meteorological variables are dependent on elevation, right? I mean, temperature we know already is dependent on elevation, but is also dependent on latitude and distance from the ocean and other factors. But maybe when you take them all together, you can argue for the lack of the need for elevation information.
I think this brings us to that discussion, Hoshin, we were having like a couple of months ago, whether to keep the multicollinearity as is in the data, or should we get rid of that and the potential consequences of doing so.
So I always thought that getting rid of the multicollinearity is a good idea, but after Allison's comment, I'm not so sure anymore.
Yeah, I think along the same lines of Hoshin, the fact that you have a positive correlation in two variables, it doesn't mean that they're totally fully the same, because they could just have different linear patterns within certain range, but then when you move to the extremes, they may be totally different. So you're losing that information that the other ones are providing. The two of them are providing in that range.
Maybe mutual information is one way to, or maybe multiple ways of looking at the relationships. This is probably, that's a very good point.
So
That's a good argument for mutual information. Yes. Praveen.
So one thing to think about is that models are information processing engines. Essentially, they are taking what is coming in through the input, they are processing it and producing whatever output you are desired. If they are inadequately processing information that is contained in the incoming signal, then the relationship of information that is contained, or the dependencies that are contained within the input, is not gonna be resolved by the models if the models are not designed to resolve them. And so throwing more information to a model that is incapable of resolving is not gonna do anything. It's like me going to a concert and I have no appreciation for the music. It's all gonna sound like a noise to me, whereas somebody next to me is gonna be jumping up and down with the beats and enjoying it. And so I'm a different model for processing the same information as compared to somebody else. All right, so if you add more and more instruments, it's gonna do nothing to me. And models behave the same way. So I think it is inadequate. It's an inadequate question to just focus on the structure of the dependency or the nature of information in the input without explicitly recognizing what is the design of the model for processing that information. And if there is more information in the input, is there an opportunity for the model to do more? So an example is, if you throw in more variables, are you trying to predict that same one single variable called stream flow? Or are you trying to predict many more other variables? In which case, just having two variables would be inadequate, right? So I think the question has to be more completely framed before we can resolve this.
Completely agree. My metaphor for this is the representation we use completely determines the questions we can ask, the analysis we can perform, and the answers we can get. So if you use a random forest approach, it permits certain kinds of questions and certain kinds of answers. And if you use a different physics-based approach or whatever, they're all, I think what Praveen is saying is that these are founded on a core set of assumptions about representation. I'm also reminded of the fact that I read somewhere, and I don't know how valid this is that they studied Western people and Chinese people, and they found that Western people processed language in the left brain as logical things, and Chinese people processed language in the right brain in centers that were more closely related to music.
And why is that? It's just the way how it is the language code, or it's our brains trained to do that, or
I mean,
it's evolution.
Sorry, it's a tonal language, right? I guess if you're talking about Mandarin, it's a tonal language. So the way that the signal is encoded.
I presume that has something to do with it, but that's a speculation. Yeah. But it has some underlying philosophical basis to it, right? I mean, cultural philosophical basis. I mean, look at the representation of language, written language in Chinese, and it involves pictorial characters and a very, very large number of combinations. Whereas we represent things in terms of, so the basic symbols are characters, which each has an individual meaning. Whereas in Western language, the basic symbols are letters, each of which doesn't have a specific meaning. You have to combine them together. So it's a rather different approach to representing language and the storage and communication of information.
So from Praveen's example, so he was talking about this concert and the instruments, right? So if I don't have any training in music, adding an instrument, it may not be significant for the outputs, right? But so, Juan was talking about his model and the inputs that he was using. So I'm wondering if having more inputs and knowing that the model is representing more processes, it is a sign of that my model is more complex and maybe is better represented. So in a way that, let's say he had 5 inputs, then he had another input and he see more better knowledge representation. So is that a metric of that the model perform better? Because in Praveen's example, if I'm a better musician, then I can, start knowing the differences between different instruments. And if there is another instrument that is added, I can just, understand, like see the difference in beat and harmony. So is that knowing that I have more inputs and I can add that to my initial conditions, boundary conditions, and my model perform better? Is that a metric of success in my model? I don't know. I don't know if it makes sense at all, what I'm just saying.
It makes a lot of sense. And if I can add another dimension to what you just said, I hate to complicate the issue, but let me add this dimension. You may have 2 people who are experts at some task in the sense that they can both perform the task equally well, a very complicated task. And one person may have no ability to explain what they're doing, and the other person might have a very, very good ability to explain what they're doing. I see a direct analogy to database modeling or intuitive modeling and physics-based modeling, which is based on the ability to explain things. It would be hard to argue that one person was less an expert than the other, but probably we would talk to one if we were trying to learn, and we would just stand back and applaud the other person for their excellent performance. Right? You can use you can use music as an example. You've got a really, really good musician, and one of them is a good teacher and one is not.
If I'm watching one play basketball versus going to one or the other for life-saving heart surgery, I think I would have different opinions about who to go to.
Well, that's speaking to domain expertise, right? Or domain limitations. Physics arguably tries to be domain comprehensive. Although if you're studying biology or chemistry, it's unclear. You would use a complete different level of aggregation or study. So an expert in physics might not be an expert in biology or chemistry. The laws operate at a different scale, apparently.
So I just wanted to go way back to something we were talking about earlier about that hypothetical or real data-driven model that does better with data that it's never seen before relative to some other physically based model, and how that kind of makes sense to me. And then it makes sense a little bit more after something that Hoshin said that's related to the Greek mythology example, which is, so I went through a modeling exercise recently where it doesn't matter what the data was, but I had 2 inputs and 1 observed outputs, and I was trying to create really bad models. So I was trying to create a bunch of models that were just behaved very differently and had very different structures and very different ways of, interpreting the 2 sources and, making an estimate, which isn't really, I'm not even training them or anything necessarily, but just a lot of different ways that you might combine those 2 sources to influence your target. And one idea that someone had was to train a model based on, nighttime data only, or, so some very small training data set, and then run it for daytime. And that would potentially create a bad model. And that actually didn't work because I trained the model on nighttime data, and it did really, really similarly to the model that I trained on daytime data. I thought there would be big differences with the weather station data that I had, but I actually threw that idea out because they just behaved so similarly that it was kind of, they were so close together, you'd have to zoom in to see the difference in the results. And that made me think that, the model structure was a huge impact though on the model behavior, which is saying something that, if you were like, oh, well, during the day, it's a multiplication of these 2 sources, and at night it becomes a division of those 2 sources. And that would be a huge difference. And that's kind of like, saying like, oh, well, when it's raining outside, that means that, Zeus is angry or something like that. And that's, like a mythological way to try to explain the system as well. Maybe in this system, it's behaving with this process equation, and that system, it's behaving with this other process equation, which is not maybe as convincing as if you had a way to represent your process that was essentially the same, which works, as I saw when I tried to train my nighttime data, and it worked on the daytime data, which means that my linear regression, which is what I was doing, is all, was a more robust way to explain what was happening.
I hope you didn't throw away that example, because that's a very interesting one.
Yeah, I just didn't use it because, I was looking for models that behaved very differently from each other, and they didn't.
but you had hypothesis, and the data surprised you, right?
Yeah. And it wasn't even a type of model that anyone would be interested in. It was just 2 data sources and 1 data target that's somewhat correlated to those 2 sources. But yeah, that kind of made me think of that aspect. There's better ways to create bad models if you want them.
That's a very good point, though. Sorry, Dan, 1 second. Because most people are always trying to create good models, and I wonder how much we could learn, not just us as professors, but students, everybody could learn if we turn it around and said, let's try to create a bad model.
I get, is the question that we're driving at, what's the criteria of acceptance for a data-driven model? Is that?
I'm not so concerned about acceptance as what we can learn. I mean, yes, you've got to accept, and presumably there is some threshold for each of us individually where we'll say, I'm going to ignore that because that's just too bad. But I don't find that terribly interesting. I want to know why it's bad, because I feel like it doesn't matter whether my result is good or bad. There's something I can gain from that. If it doesn't as in Allison's example, if it doesn't conform to my expectations or my predictions about what is going to happen, then it means there's room for me to learn something.
Well,
But it is,
I'm wondering if the scientific community is forgiving enough for let you study a bad model and then publish it. It would be not, I mean, it would be a great idea just to publish why a model is not representing, you know, any knowledge and how bad you work on it or how bad it is compared with others. But I don't know, you know, as a young scientist, that kind of publications may not be, maybe rejected or a proposal coming from there.
I'm going to send you guys, I'll send it to Leela and she can send it out. I'm going to send you guys a copy of that paper that I sent to Praveen on crashing the barriers of meaning in AI. And maybe if you guys agree, it becomes something we can talk about later. But one of the comments that the author, this is a result of a workshop held at the Santa Fe Institute, okay? And one of the points made by the author was that when we do benchmarking of data sets, we use data sets as benchmarking nowadays, for example, ImageNet or whatever, or in Freddie Kratzert's data, they're using the, what's it called? The watershed data set for the continental US. Camels data set, yeah. And one of the points that somebody raised in that meeting was that the use of these benchmark data sets drives incremental progress because people are just trying to improve performance on that benchmark. And then they're pointing out that this becomes limiting in itself, and that maybe instead of having one big comprehensive benchmark, we should be constantly throwing away the old benchmark data and creating a new benchmark data, because we want our model to not just do good at that particular data set, we want to learn generally, right? And also points out that people who try to do work that's not along the mainstream line, which is making incremental progress, oftentimes have a hard time getting published. And I've raised this discussion with Praveen and with Martin and others in the context of WRR. Like, how do we, you know, how do we? Why is it that papers that are not terribly innovative sometimes are easy to publish, and ones that do something which raise, you know, where people explore things that other people are not looking at, sometimes get really bashed down and get a hard time, you know, being published. So anyway, Praveen, did you just?
The calibration problem, Hoshin, people's minds have been calibrated with the traditional science, but then when they're exposed to something different, they might not react with the same surprise.
And there's so many examples in science, like when the idea of the planet being a bunch of plate tectonics, you know, when that came about, that was soundly rejected by the scientific community. You know, it took a long time before it. So you know, we have a history of doing that.
Well, more recently, the data assimilation by Kalman. I mean,
data assimilation by Kalman, and even our own experience with trying to raise the value of information theory as perspective, which has received strong pushback, all of which was good, but it is part of the the culture of our disciplines, right?
And also the psychology of incorporating new information. I mean, I guess I've been reading Daniel Kahneman, and he talks about how we form our beliefs, and we, as in anybody, as humans, how we form beliefs, which is based on the opinion of others as opposed to based on information that's presented to us. And so if we are presented with new information that goes against an existing belief, then it becomes like a personal insult, because we formed it based on someone we trust and the opinion of someone we trust and love. So I
like to call these things holy cows, of our science, right? So one of the holy cows of our science is that machine learning, artificial intelligence, whatever, when you build models, the training and testing data have to be independently and identically distributed from the same underlying data generating process, right? The training data and the testing data have to come from the same process for a fair model development. But for learning in science, you actually want to test your model on data which is completely different from what you trained it on. You could argue the converse, that that's when the maximal learning will happen, right? I'm sort of arguing for both. I'm saying you need both, right? You need one to help you develop your model, but you can't stop there, and we should never let somebody stop there. You could think of a paradigm in publishing where the people developed a model and then demonstrated how good or bad their model was on some ugly data set. We could create a journal around that.
So Hoshin, in a way that will be a topic of counterfactuals, right? So
nice.
I think
Very
it's
nice.
related. And something even more scary is in the theory of counterfactuals, the knowledge, I mean, has a property and it has to be transferable. So in a way that if your model works very well in a certain domain, so if it doesn't work well in the non-tested environment, then that is not a good model. It's not information itself.
Well, it doesn't necessarily mean it's a bad model, but it does expose its limitations, right? So,
but it wouldn't be information. It wouldn't be information that can be transferred. Therefore, the model by itself doesn't.
Well, the question might be how much is transferable. But let me pose a hypothetical where Hernan and Roy decide to collaborate on a research project, and Hernan does the model development with whatever data sets he has, and he then sends the model to Roy, and Roy's job, this is the generative adversarial context, Roy's job is to find data sets to test that model on, which reveal all of its weaknesses. And then he sends it back to Hernan, and Hernan says, okay, you fooled me. Okay, I'm going to come back with a better model and I'm going to send it to Roy. And Roy says, okay, that did better, but I'm going to find this other data set and I'm going to show you what's wrong with the model, right? In a sense, that adversarial process is supposedly built into our scientific development thing, but it takes place over very long periods of time, and because there's not a procedure in place where you can submit a paper and then somebody independently tests your results, right? In another context, maybe in medicine or other places that happens a bit more.
So this is a great analogy, Hoshin, and makes me think about the next generation of models that should evolve, should be learning all the time. So we don't have, so we can, so they can make decisions on their own and how to better represent things inside, and how to actually ask the human for better data. You can actually tell the person, hey, go get some interception data or snow accumulation data because you're giving me crap, so I can't do more. Because I'm finding here that you have a lack in this area, I can't represent it well. Even though if I improve the geometry of the data and the triangles are even smaller here, there's no way that I can represent better things. So you need to go collect data on this. So this would be a kind of a morphing model type of.
Praveen, maybe you want to dig it out of the archives and have this group work on that proposal for a generative adversarial approach to workshops based on generative adversarial approach.
Yeah, I think I've thought about it, and we should try it again. The problem is that the adversarial nature of reviewers, they don't recognize the generative process.
We could try going to a non federal funding. We could try to go to private funding.
Yeah.
It was an interesting enough idea. We might be able to get it funded, to do workshops in that context.
Yeah, I mean, the thing is, these discussions and our prior discussions are essentially pointing to the deep philosophical advantage of this idea of generative adversarial approach, right? Where you are trying to improve. So a lot of the discussions we have had with the duality and things like that, I mean, those are essentially two different representations, and we can find things. So, I mean, going back to the example of light, there are some things explained by the wave nature, and the other thing is explained by the particle nature. And we see that kind of thing all over the place, right? So if we could bring that into our thinking in an effective manner, we would be able to resolve a lot of things in there. So there is a lot of value to following up on that. I agree. Okay, we have 15 minutes left. What do we want to do with this? I mean, this discussion has been awesome. So we had a third topic, which is to on the, what is it? Scientific discovery based on information theory, machine learning, AI. Maybe that's for another time. Is there anything, I would suggest we defer that for another discussion and try and close any gaps in this two topics that we've been trying to do. I don't think we have explicitly touched on the intersection or the union space between information theory, machine learning, and AI. We have basically housed that all under data-driven in there. So we've touched upon that, but I think one of the thoughts that I had was that based on these readings, which by design, when we did this last year, we said, let's try and train a lot of literature that we don't normally read on a regular basis, right? We go out and see interesting ideas that might be there, which might influence some of these things. And the goal of today's was basically to at least bring into the force some of those ideas. And we have done that, but I suggest that in the next 10, 15 minutes we have, maybe we look back and see if there are other things that we might have missed to integrate in here. Does anybody think of other things we read and characterized that we should think about?
I'd also like to encourage Afifas and Sophia and Tarun, who have been very quiet, to also share at least one idea of one thing which of the discussions and readings that influence them. Yay, Tarun, go for it.
Hey, hello. Yeah, it's like the discussion is very great so far. So I joined PhD in 2019 with Professor Praveen Kumar. And I'm also working on this information theory part. And it has been very nice to know about so many things because it was very new when I came here. When I joined, I didn't know about information theory at all. And now at least I know there are so many things which are going on a different perspective. So it's been good since then. Probably I will share a few ideas which, like, not ideas, but the questions in the future, if I have any.
Okay. Sophia?
Hi, everyone. Kind of been more quietly observing the last few sessions, but my research is kind of focusing on the comparison between like physically based models and machine learning models. So it's been really interesting to kind of hear everyone's thoughts and how that has intersected with their research as well. I've had some challenges kind of trying to apply a machine learning model trained on one data set to an area without a lot of information. So kind of pulling attributes and stuff from different sources. So that's something that I've been working on over the last few months.
Do you think you'll have something you can share with us sometime?
Hopefully soon, hopefully in the next few months.
Sure. I mean, even if it's some preliminary results, that would be very interesting.
Okay, awesome. Yeah, I'll see what I can pull together and talk with Stephen about what we're working on.
All right, thanks.
Yeah.
Afifa? Are you there, Afifa?
Hi, yes, I am. So yeah, I mean, my research is not directly related to the information theory thing. So yeah, it's pretty much same as Tarun. I didn't know almost anything about information theory, but yeah, I got exposed to nonlinear dynamics after coming here in a course conducted by Professor Kumar. And yeah, I'm interested to know what's going on from in terms of application of information theory in different domains. Yeah.
Thank you. So back to Praveen's question, how has this series of discussions changed you? How you think about things in your work? It could be the same as somebody else, but it's useful to know how it's directly affected you. What stuck most in your mind?
I can go first, I guess. For me, my background is civil engineering, so I really didn't have a good grasp on like what information theory meant and like how it tied into like my work in water resources. So even just like attending these discussions and hearing a lot more about like how information content plays into the way that we use data in our models has been really, really interesting and kind of given me a lot more perspective in being more intentional with how I develop my models, not just what's out there, but maybe what am I missing and what is my model missing or not capturing.
Great. Roy?
Sorry, Hoshin, I was responding to an email. So like how how the discussion sort of, so what was the role of the discussion? What was that the question?
How has it influenced your thinking? What's the single idea, most impactful idea that has influenced you?
I think there are a lot of them. I have to be honest, I didn't read all the papers like equally carefully, but I think there are several things that I found, very, very interesting. And one of the reasons why I am also a part of the group is because, I am also bringing information theory concepts in my research group. So my students will also be working on, some of these concepts. So we are also sort of setting the stage for that. So so this is very timely and very, very helpful for me.
Yeah, but it's okay to say there's a lot of them, but mention one or two.
So, the idea of like how, so how can we incorporate useful information from huge lot of data we have? I think that's an interesting problem that I'm that's where I think that's where the third sort of point that Praveen had there that relates to that, like how can we extract useful information from a bunch of data. I think that's where the information theory and machine learning can really come close. And then getting into the idea of like, okay, we have the data, then how much what different ways we can use that data to construct different models. And then and the other way around, and what, how can models infer us to see what type of data we have to collect. So I think so there are several things that I think I found super interesting. The notion of like relating information theory with uncertainty, that's Alice and I have been discussing that for some time now as well. Yeah. and general like information theory metrics, like simple metrics, like their potential in exploring nonlinear relationships, the information gain and other things. I think there's several avenues that I'm very interested in. Yeah, and this, of course, this discussion has helped me sort of find these interesting papers that you all have shared. So I think that have been very enriching.
All right, I think you were jumping up and down a little bit.
I think there is one
Laura?
more topic. Oh, I'm sorry.
Oh, Leela, go ahead.
I think there is one more topic that we didn't touch, not even the tip of the iceberg on it, and it was the quantum information. So probably from a philosophical perspective, we can start exploring that concept, and yeah, in the future readings. I don't think there is much about it, but yeah, we can start exploring that topic.
So given that I purposely chose to avoid that chapter, when we talked about it, and you're interested, would you be willing to think about making a presentation based on that chapter?
Yeah, it would take me a while
Whenever
to
you're
get
ready.
the insight and be able to share it with the group, but yeah, sure.
Perfect. Yuan? How is being part of this discussion group affected the way you think about your work and about science in general?
I think overall I learned a lot because, yeah, you know, every week I listen different paper and presentation, and everything is really new to me, and you know, I think.
Just give us one idea which comes at the top of your head that you liked.
So I think I was is the symbolic regression, because we just submit a abstract to AGU, and I think that is something in between that we can try to bridge the gap between the deep learning and physically based model. Yeah. Otherwise, you know, because the research we have seen so far is not really trying to break the framing of each representational system. I think that would be something possible to make this real. Yeah.
So this was influenced to some extent by the Tegmark paper that Dan covered. Yeah.
Yes.
Perfect.
Ocean, I think in my case, you know, coming back to the bad models and how can you incorporate them in your research, I will try just to be more lenient with my physically based models and do not force them or punish them because, you know, because the data is, or the outputs are not representing the data, right? Probably just looking at what is valuable versus the loss of information, and stop like breaking that paradigm of uncertainty. And it's exhausting, to be honest. so it may take me more time to publish my manuscripts, but from information theory, you may be able to justify it from another perspective.
So can I ask you to think about and maybe bring back for discussion a question, which is, what is a meaningful basis for testing physically based models?
Are you asking me right now to answer?
I'm not asking you to answer the question right now, but it is a question that has been in the back of my mind, which is, instead of just saying, I've got to get the best mean squared error or whatever, when you evaluate a physically based model as opposed to a database model, right? What constitutes a meaningful evaluation, something which helps establish confidence in that model?
That's very difficult.
I know it's difficult, but
I cannot answer that because you
but
either.
that's what I
Right.
just want you to think about it and maybe bring it up for discussion at some other future time.
Sure. There may be already papers on that, but validation is just brutal process that you have to go to in order to publish, especially in my area.
The reason I'm asking is that Ben Ruddle and Reed Maxwell and Laura Condon and others are trying to get a paper published based on the idea of benchmarking facilities, national benchmarking facilities. And so a very valid question that would arise is then what do we mean by benchmarking? Right? How do we establish validity? And have we had enough of a discussion about what that means?
So I think this will also depend on models, because even between physically based models, the representation of physics will vary. So so what you can compare will depend, but definitely mass and energy balance for sure. Looking at the seasonal cycle, the variability, those type of things, those are standard diagnostics we can do. But at the end of the day, I think it's still a model specific question, because my physically based model may not actually have that process that yours have, for example.
But don't you think that conservation is a low bar? I mean, every model into comparison I've seen, whether it's land surface models, climate models, everything, they put conservation as being the foundational thing, and then they
it is a low bar. I think it's necessary also, right? I mean, you have to go and up and beyond that, but you still need that.
I'm just saying, isn't it time to go beyond that? Yeah.
Yeah, definitely. You can also do different types of signatures. So even within model, different interrelated processes, you can actually calculate signatures and maybe compare that with some way with physically observed. Again, there could be so many different possibilities. Yeah.
I think we're running out of time. Anybody else? Dan?
I guess in general, I want to say that I find a lot of the time reading some of these papers can be very intimidating. And I find that coming to this group, it brings it down to earth a bit for me. And I really appreciate everybody's support.
So Praveen, what do you suggest we do next?
Oh, I think we should probably figure out some additional reading or discussion ideas. I mean, we didn't get into saying what are the opportunities where this group might be poised to integrate and pursue, right? I mean, I think we have done a lot of reading, and what we should do is continue to do that. But I was hoping that there might be more targeted approach to doing this, saying, okay, given that we read 15 papers in addition to whatever else we are doing and so forth, here is what we see as some avenues, not thinking of them as research avenues, but discussion avenues, just to clarify in our mind some of these things. So I was just wondering if it is worthwhile to continue this discussion one more time, but with that as a target, rather than retrospective look, forward look, and saying, okay, here are, I think, the most compelling 1, 2, 3 questions that we might want to think about, and then see how we evolve towards that. Does that make sense?
All in favor.
So
like the idea.
What might be helpful is basically we have created some very good notes, I think, but I mean, if people want to just step back for half an hour and put down their reflections or edit those notes based on the reflections from this meeting, that will help. And at the end of it, you can say, okay, here are 1, 2, 3 questions that come to mind, which would be great to pursue, not just as a group. I mean, not just as an individual, but I mean, think about big ideas, right? I mean, things that one person as an individual won't be able to pursue, but would be very delighted to be part of a group if that group pursued that question, right? So I think trying to think big might be a way to go forward. So let's see if we can do that through reflections on today's discussion, and then going forward in the next meeting, if we can organize that. Right.
So Praveen, are you referring more towards like thinking about grants that we can apply potentially in the near future?
Funds are an outcome, not the primary reason. So I think the way we have done this so far, it's been great that there has been no money on the table. So we are pursuing it for an intellectual excitement. And I would say that we keep that in as our primary goal. If there are things that we can peel off to pursue as smaller groups, I mean, so be it, right? But I think I'm excited about the intellectual engagement. And so big ideas that will keep us excited, talk about it, think about it, get everybody to this kind of a gathering every 3 or 4 weeks, right? I mean, and people are excited about it and putting in time and effort. I think that is of significant value rather than a proposal or a grant in there. So I think that's what I'm thinking.
Just speaking for myself, the reason I went into academia is because I wanted to be able to do this kind of conversation. It was not so I could get money or become famous or any of these other things, right? It was to be able to meet minds and have these kinds of interesting conversations, which is why I think most of us are in this field. So.
And as Dan said, I mean, I think we should all think of this as a safe space for having the conversation. There is no judgment, there is no criticism, there is friendly adversarial characterization of ideas so that we bring out more nuanced things in there. And I think that's the best thing that can come out of it.
Yeah, agreed.
In that regard, I'll just pat ourselves on the back that usually when you get people into groups, you break them into 4 or 5 to do discussions. I'm really impressed by how, as a fairly significant sized group on Zoom, we're able to, do this. This is amazing.
Okay, I think let's continue this in it's 3 weeks, right? Every 3 weeks, so we'll do that. And Hoshin, I mean, this other thing regarding the issues related to meaning and all, I mean, that could be potentially included in our discussions instead of forming a separate group or things like that. Yeah. Hoshin, you're muted if you're talking.
I said, I agree. Let's do it. I was just trying to see if anybody else would bite. I will send, you already put the paper in there, but I will send my summary to Leela to distribute.
Yeah, and I think there is a very nice book by Melania Mitchell, which just came out a month or 2 ago on information, and started reading about it. I'm probably halfway there. It gives a nice perspective. I think it's on AI, not information.
Okay.
But it's.
Are you by any chance a member of that Association for Advancement of AI?
I'm not. I looked at it. I saw your email, and I looked at it, but I haven't spent time on that yet.
Yeah. I'm tempted to become a member. It's $145 a year.
Okay.
So I might, and I'll look into it anyway. Just because it seems like they talk about interesting things, and in a sense, it's a small group. They've got their own little small group, and their workshops are all by invitation only. But at least we can get in perspective on what they're talking about. In a sense, our workshop, our discussions are very similar, so I can't complain.
All right. This is great.
Thanks, Praveen. Thanks, Leela.
Bye, everybody.
Thank you.
Bye,
See y'all later.
Thank
Thanks.
you.